We've been talking about logarithms. So where did this idea of logarithms come from? Well, it came from a gentleman by the name of John Napier in the early 1600s. It was a way to connect exponential functions together and solve them using the idea of logarithms. Now, logarithms have a base of 10, unless we state it differently. But what if we used a very special base? That's what we're going to look at here. So let's revisit the compound interest formula that we've talked about a few times already. So compound interest, we have an amount that we're going to accumulate. We have a certain principal, P, and we're going to keep that principal, and we're going to add to it some rate over time. Now, our amount that we accumulate, if we compound it, then if we compound interest, let's say, then we're going to do that n times a year. So our formula changes a little bit. So what if we took just something simple like $1? And what if I said you're going to get 100% interest for 1 year? Well, that means your money is going to double. So at the end of the year, you would technically have $2. But if we think about nature and how things grow or double, it just doesn't all happen at the end. For example, you're not, you're not 3 feet tall, and then all of a sudden in 4 years, you're 6 feet tall. It happens gradually over time. And that's how compound interest really works as well. So I've got this chart for us. So you've got $1, you're going to compound it 100% interest for a year. So what is the value at the end of 1 year if interest is compounded? What if we did it quarterly, monthly, semi-monthly, bi-weekly, or daily? Well, we know if we did it over the course of a year that it would be worth $2. Quarterly means we would do it 4 times over the course of the year. So if we go ahead and assume that this is our n value, the number of times compounded during the year, and it's 4, and we plug 4 into the formula up above, our dollar is going to end up to be worth $2.44. Much better than the $2 that we had if we just got the money once and compounded once at the end of the year. What if we figured interest in every month? Which means we would get interest at the end of January. And then we would have interest figured on top of the dollar plus the interest we earned. And it just keeps growing over time. Well, if you do the math on that, our dollar compounded interest every month is going to become $2.61. Now, semi-monthly means interest is going to be figured twice a month. So 12 times 2 gives us 24. And so, using the formula again, our dollar would turn out to be $2.66. Getting better. Now, bi-weekly, there's 52 weeks in a year. So every 2 weeks, if interest was calculated, 52 divided by 2 is 26. So does that make much of a difference? Well, it does a little bit. It goes up to $2.67 at the end of the year. Now, if it wasn't a leap year and we did interest 365 days of the year, our dollar would be worth $2.71. So our interest that's compounded looks like it's increasing, but maybe it's getting close to something. Jacob Bernoulli thought the same thing. And so this was a problem that he worked on, this compound interest problem, and it originated, or I guess not originated, but ended in a number. And that number is E. Now, E is an irrational number, like pi. It doesn't have a pattern. It goes forever. And it's a decimal that is approximately 2.718288182, and there's no pattern really to it. So, when we think about E, which is known as Euler's number, named after a gentleman by the name of Leonhard Euler, E is very useful to us. In fact, we can treat E as a number that's used in logarithms called the natural logarithm. And the natural logarithm is denoted by ln. Now, ln is the same as a log with a base of e. Now, logarithms are used, in fact, natural logarithms are used in lots of different things. Some of those things would be the magnitude of earthquakes, like the Richter scale, intensity of sound, or the brightness of a star. We've already seen how E can be used as a reference when we're compounding money at a given interest rate. It deals with power and voltage and radioactive decay of elements and other things that might be changing at a non-linear rate. So when we're working with the natural log, these are some things that we can go ahead and look at with it. If we have the natural log of e to the third, and we want to find out what the value of this is. Well, this is the same as the log base e of e to the third. And so it's basically saying e to what power is e to the third? Well, that's 3. So we can go on and say that the natural log of e to the 9th, let's say, is 9. Now, logarithm properties work whether the base is 10, 7, or e. So if we see the natural log of x cubed, we can rewrite that as 3 natural log of x. We can pull the exponent of x out front, just like we could with regular logarithms. Now they can be solved too. For example, if we have an equation like 3 to the x is equal to 5, well, we could take the log of both sides to solve for x, but we could also take the natural log of both sides. This allows us to pull the x out front, and then we can go and divide by the natural log of 3. So natural logs can be used in a lot of different ways exactly, I should say, except with the base of e, like logarithms can. So when you see the natural log, the ln, next time on your calculator, know that that is a logarithm that has a base of e and can be used in a wide variety of things moving forward as you advance in mathematics.